Okay, we've seen in quite a few places that computers work using purely ons and offs. There are some very niche cases where they actually can use other number bases, but pretty much every computer you will see in common usage now works purely off using ones and zeros. This is called a binary system, and we're going to build up some of the sections needed to work on it. So what we're going to do is going to go through the worksheet very quickly. I'm not going to do everything, but I want to show you how things work and how some of the tools work. There's two websites you're going to use. You can use to do the worksheet. One's Logically, and one of them is this Logic Game Simulator. This one's a little easier to use in terms of selecting, but the features of Logically mean I'm probably going to use that one for mine. And that's actually what created all the pictures that are in this video. So let's go through and quickly talk about what binary means. Binary means one of two states. That's what the bi part means. Bi means two. Nary, a number system. So this is a two-number system. The numbers are 0 and 1. There's lots of different situations where we might talk about them. I'm going to leave them for you to fill in what logically we should go in, but things like off and on. Off is traditionally taken as 0, on is taken as 1, yes and no can be done. And the ones that are important for computers is the voltage and the logic. And the voltage, we don't choose a specific voltage. Generally there's a point where we say it's above. It used to be fairly common in computers that they were using 5 volts. If you got a voltage coming above about 4 volts, it was treated as being high. If you got a voltage below 1 volt, it should have been low. If you had something in between, you had a problem with your circuit. Modern computers, they've got a lot lower energy requirements and much smaller transistors. That means the voltages now, to stop overheating, need to be a lot lower, to the point where I think the latest Intel processors are using about 1.1 volts internally as high and about 0.1 volt as low. If you wanted to do a denary system, a level 10 system, you have to have 10 different voltages. And then you might realise that when very early computers, they were working with hundreds of volts, so they could get these clear, that's a 1, that's a 2, that's a 3. They used loads and loads of power. So one of the trade-offs was to reduce the power requirement. Let's reduce the number system, and we're now going to use a number system using zeros and ones. A couple of lessons time we'll be doing some arithmetic with this. At the moment I just want you to get the idea of the logic that's going on. So we're going to look at the logic. Traditionally inputs are called A, B, C, and the outputs, traditionally you've got a single output of Z, but you might have a few more. If they haven't got special meanings, you'll get Z, Y, X going backwards. There are a few that sometimes have special meanings. So C is 1. C in certain circumstances can mean carry. That means you have to be careful in your circumstances. But for our switches and everything we're going to do, we're using A, B and C. So let's start with the simplest gate, and it'll give me a chance to show you how we can use this Logically website. I'll do this quickly also with the LogicGate simulator, and we'll whiz through. So you need to fill in, anywhere you see a box which is blank, you need to fill something in. Well, what things can go into a NOT gate? Well, A could be 0, or it could be 1. We don't consider anything in between. Anything in between there should flag some errors elsewhere or your computer crashes. So we're just considering 0 and 1. I need to build the circuit, and the circuit consists of a switch, a connecting cable, a NOT gate, and to see this is a NOT gate you have to look at it very carefully and make sure there's this dot on the end, and then connect to some form of output so you can see what's happening. So let's do that quickly and logically. This is the Logically page, it's the demo, and you see down the left hand side we've got various tools, and we've got a thing called a toggle switch. That's the one I'm going to use. It just allows me to turn things on and off. Push buttons, if you're not actually pressing it. I'm going to give it a proper name of A. So it's often the option, so I'm going to call mine A. So I've got a toggle switch, and I need the output, a light bulb. Now if I place those quite far apart, I could probably keep using them. Output names from the end of the alphabet. So this is a Z. We need to connect. Now the logic gates are in this section here. Don't worry about flip-flops. You'll be talking to Mr. Scott about those if you do computer science or GCSE. These are more to do with actually proper electronics, where there's pull-up, pull-down. We'll look at one example where there's something going on with that later. So I want to build a NOT gate. So have a look through, or take the command, put the NOT gate in. Notice the dot. If you don't put the dot in, I'll put another light down here so you can see what happens, what the buffer means. The buffer has a particular set of uses. We'll call it Z2. And now I need to connect these up. So to connect them, you drag the bobble from the end to where you want to connect it to. And notice when I was connecting the bobbling, it knows which ones are expecting inputs and it's showing it to me. So I can do an input to that one as well. Then coming from that one, I want to put it into that bob, and I want to put it to that bob. So this is currently off, it's not coloured in, and the output is on. Switch the switch, now it's coloured blue. Everything that's on, has power, is shown. And now my output Z is off. And if you have a look at the other bulb, this Z2 one, the buffer has the same state. It's there for a couple of reasons. We build them into circuits for a few reasons. Normally, to make sure our voltages stay the right level. So if you've got lots and lots of connections coming out of one, you gradually lose power. And the buffer allows us to boost that power. The other one is certain circuits, there is a little bit of time delay going across the NOT gate. And if you've got something else going on, you want to keep it in sync, you might want to put a buffer in just to maintain that same transition time. It is used in certain circumstances electronically, but nothing you need to worry about. So this is my NOT gate. So input, not lit up, so it's off. The output is lit up, so it's on. So I put into my A, 0, my Z is 1. And when A is 1, my Z is low. Okay, so that's the truth table. It tells me what happens when I see this diagram, this little triangle with a dot on the end. Whatever this is, it turns it to the other way round. You've got to build this one and work out what the circuit is. Now, one problem with using logically is it actually tells you the names as you go through. If you use the logic gate simulator to try and do it, it's got a couple of little bits to add. Rather than a nice graphical interface, you have to drag things around. Come on, give me the drag. Or is it not dragging? Oh, there we go. Right, so you can't drag on the name, you have to drag in the box around it. So I'll just do the next gate, and the next gate is this D shape. And the D shape is called an AND gate. So I add the node, it creates my AND gate, I drag it through, and just like with logically, you drag your connections from one point to another. Drag your output, and then you can click on things and see that's off, that's on, that's off, and as I click through, suddenly you see outputs. You just don't see these connecting lines, so you can't see what's happening. All you see is the overall result, which is one reason why I'm avoiding using this. So work through your worksheet, putting all the numbers in, describe what happens. So this one I should really have put in a little note. I'll try and put a box back in for you. I should say, take one input and flip its output. Okay. So it goes to the opposite state. These are called states. This is a low state, high state. This is a high state, low state. So this takes a low state, turns it into a high state. You've got a number of circuits to build, and you've got a fairly complex one here. Do take to do it, because you'll find this is actually the same as one of these other circuits are further up. And the reason that's important is when we come into this section on the advanced stuff,